Hans holds a Master's in Operations Research from UNISA and an MBA from the University of Pretoria. Now, in this chat we just had, he referred to his career at the Council for Scientific Industrial Engineering, or in short, the CSIR, for over 38 years, and he retired already in November 2011. It feels like yesterday, but it was 14 years ago.
Yeah.
And at that stage, Hans, you were the executive director of the CSIR Built Environment.
Yeah.
After Hans's retirement, he acted as a consultant, and you are still acting as a consultant, Hans?
I'm not, but I was just telling Dave, I have an association with the University of Johannesburg. With one of the departments. I'm an associate researcher in that department.
Okay, and you are an associate researcher with the Institute for Transport and Logistics Studies that you just also referred to.
Yeah, that's actually the one.
Yeah, okay. So that is associated with the University of Johannesburg.
Yeah.
Okay. And you have a very wide experience in operations research and logistics or supply chain management, with in-depth knowledge in optimization, modeling, simulation methodologies, and I want to say, etc. Hans has published over 40 papers and chapters in scientific journals and books. He presented 120 papers, I want to say more than 120 papers at local and international conferences. And he reviewed more than 150 technical books. From early as 1973, Hans has been a member of the Operations Research Society of South Africa. And he fulfilled many different roles throughout the years. In 1987, Hans was the president of ORSSA, and again over the period 2001 to 2003. He's a fellow and is an honorary life member of ORSSA. And he is a fellow of the International Federation of Operations Research Societies. Hans, this is an impressive resume. So we're really looking forward to your taking us back through the career and through the early ages stages at the CSIR. From 1973 to 1986.
Okay. My agenda is the following. I'll talk a little bit of the early years and possibly, maybe a bit too much about myself. And then, really go through a whole range of different projects that I was involved in those early years of the CSIR. So I'll start off with, I grew up in the Free State, Viljoenskroon, matriculated in 1966. And then I joined the Air Force to do pilots training. I was fairly young and I didn't really know what I wanted to do. But I knew if I finished with my pilot's training, I could go to the military academy. My parents had two sons that there was no way in which they're going to afford two boys at a university. So the military academy was great for me. Did a BMIL BSc with physics and maths, and I finished there in 1970. Now, maybe just to say that a picture that you see on the left-hand side is a Harvard, and that was the aircraft that I was trained on. And the picture on the right-hand side at the bottom is a Vampire, and during the holiday break in 1970, the third-year students, Air Force students, got a conversion on this aircraft. It's a jet aircraft. But during that course, I started picking up some health issues with my knee, and then I was made medical unfit. I joined a unit in Pretoria, Joint Air Reconnaissance Intelligence Center. I also tried to do an MSc in physics at University of Pretoria, but I think the jump from Physics 3 from military academy to UP was a bit too much. And then in 1972, I started with OR at UNISA. And the guy who influenced me was Duister Vries, who was actually a navigator, and he was my lecturer in aeronautics at the military academy. I had 2 operations, started flying again with 4 Squadron, and the last time I flew was in October 1972, and the health issues reoccurred, and I was young enough and decided to leave the Air Force. And I then joined the National Research Institute for Mathematical Sciences at the CSIR. Now, I was a pilot. Here I moved into a research organization with basically no OR training. Joining an OR group, just started doing OR at UNISA. And it was really, I think, because of my military background that I was sort of appointed there. Theo Stewart, as most of you know him now, was the only one in the OR group. The guy who actually referred me to the CSR was Jos Stroblaar, who was professor of OR at UNISA at that stage. And it's only in the last week or two that I thought, but when I went to see him, he must have been president of ORSSA, because he was the second president of ORSSA in 1972. So at NRIMS, I first had to get computer literate, and then started getting involved in military-related projects and the Maize project, and I'll talk about them just now. I shared an office with Theo for a couple of years, which, was quite special. A number of people were appointed during that period. I'm sure most of them you don't know. Duister Vries, who was at the academy, also joined the CSIR for a while. And then onwards from 85, there was a lot of other youngsters. I make the point, I joined ORSSA in 1973, and it happened in the way that Theo Stewart came to my desk and said, "Here's an application for our society. Will you fill it in and hand it back to me?" I had no choice. And I then attended the first OR conference in 1973. And after that, I think all the conferences, it was something like 50 conferences that I attended consecutively. And there's my studies. Marthi mentioned it. The MBA was for me very important because it actually helped me to get an understanding of where my strengths are. And that was, hugely beneficial to me in the rest of my career. Still at the CSR, Theo became head of the OR group as it expanded. Later on, there was statistics that joined the group. We had weekly work discussions, which was incredible. Statisticians and OR people talking about the work that they were busy with. And you're sitting there with top guys and they're giving you inputs and their views. As youngsters, it was a bit nerve-wracking to give a presentation there. Theo then was promoted to director and head of OR and statistics, and he resigned in 1984 to go to Cape Town. I'm sure there was some politics in the process. Somebody lower than Theo was promoted, as the director of the then institute, and I don't think it went down very well with Theo, but I think he ended up at the right place. Paul Fatty then took over from Theo, and then I took over in 1986. There was a whole range of changes taking place at the CSR during those years. Up to about 1982, CSR was almost 99% fully funded by government. And the government said, well, that can't carry on. And the organization then went through a whole strategy session and had to become much more market-orientated to generate their own funds. Many of the researchers left, and there was even no longer a home for physics, chemistry, and mathematics at the CSR. But the CSR suited me quite well. I never really considered myself to be a researcher. So it really suited me well. So that sort of is the early years. Now I'm going to start talking about projects. The first project OR project that really started at the CSIR was in the wargaming environment. Was called Project Sening. It is part of the senior officers or staff training course of the Army. It was originally a rule-based, hand-driven war game. It was conducted on an annual basis, and the CSIR, as I said, drafted the rules, and we assisted the referees during those games. It's two forces, the red and the blue force, who compete with each other. The times that I was there, it became quite emotional, and the one wanted to win the other one, that kind of thing. But there was all kinds of rules associated with these war games: mobility, sighting, the terrain that the operation or the battle was taking place. The staff of the Army College presented a scenario to the two forces, and they then had to assess the situation, set up their forces, and then, the battle started. And based on what units they had, based on what firepower the units had, and how they sort of assembled their fighting units, and how they conducted things, based on that, the referees then gave the outcome. There wasn't always agreement on that, but that's the way the war game sort of happened. We started partially programming it. I can recall that I did some programming in Fortran, sort of really just the combat side of things, where you had to do calculations. And then somebody joined the CSIR who just returned from the States, and the computers technology improved, and we got a mini computer. And this guy said, no, let's develop a whole system dedicated for wargaming. Even the operating system was dedicated for the war game. And we developed this all in a machine language. My role was really around the combat-related components. You worked with bytes and bits and half bytes and I don't know what. It was quite an experience to go through that. I make the point there, don't debug software under pressure. We were at the war game, and there was a bug in the software. And it wasn't in my sort of piece of the programming, but the other guys spent one night, right through the night, trying to find the bug. They couldn't find it. The Monday morning when they arrived at work, within 30 minutes, they had the bug. Just the fact that they were under pressure sort of didn't help much. Then, as I indicate there, the wargaming sort of took over by the defense force. The CSIR people was still involved in various ways over the years. The guy who was heading the OR Wargaming Center was actually a guy with a PhD in operations research, which was also quite interesting. He never actually attended our conferences. I'm running through projects quite quickly. Then there was a simulation model for strike aircraft. Now, the Mirage 3, I don't know if people can recall that, came to the end of its lifespan, and the Air Force had to get a replacement. Now, at that stage, there was the Air Force, but also Arms Corps, and Arms Corps was really helping the Air Force to try and find, what would be the most appropriate strike aircraft as a replacement for the Mirage 3. And they said, well, let's develop a simulation model. And we use the simulation model to compare different strike aircraft. And it was decided to develop a standalone simulation. We didn't use a package. I think Simon was the package that was available, but we wanted to make sure that the people involved could do whatever they want with the simulation. So I was the one who developed the simulation model in Fortran. My Air Force background did help. it was a fully operational simulation. You have a squadron of 16 aircraft. There was targets in the neighboring countries, targets that we got from national intelligence. And I think we operated from, or the simulation operated from Petersburg. There was an Air Force base. And, when your vehicles take off, there might be interception on the way to the target. All those things was done with random numbers. They had to go to specific targets. There was no guarantee that you'll hit the target. Also, computations with random numbers, whether that actually happened or not. Yeah, so different threats were defined, and a whole number of different aircraft with all their capabilities, their parameters, payload that they were able to carry was sort of used in comparing the aircraft. In the end, because of the political situation, South Africa could never buy any new aircraft. And that led to a very close collaboration with Israel, where Israel also changed their Mirage 3s to the Kafir. And our Mirage Cheetahs is very similar to the Kafir, at least as far as the engines is concerned. And what was interesting, and I think people might find this interesting, is that Johan Pelser, the husband of Winnie Pelser, he was actually the chief engineer on that project. I thought of something that I needed to say, but no. So this was quite a nice, the validation. How did we validate the model? We used the 6-day war results that the Israeli Air Force could give us. Now, it's quite interesting. With a squadron of 16 aircraft, within 3 to 4 days, you're down to having about 3 serviceable aircraft. Things actually go wrong when you're in a war kind of environment. And our simulation actually was very, very similar to what they found in the Israel sort of war situation. And that gave us confidence in the model. Then we also developed a long-term planning model for the or system, decision support system for the Air Force, looking at, how long, well, the composition of the Air Force at that stage. They had over 350 aircraft. I read yesterday there's 6 operational aircraft in the Air Force currently. Those days they had a big fleet. All the aircraft have different lifespans. They had to be replaced. Aircraft had to get major services. All those things form part of the long-term planning decision support system. Now, in this case, we had our client was a fighter pilot, and our system was not used. It was a massive, or in our terms, quite a failure. And what we only realized at the end of the project is that this guy, fighter pilot, is hugely afraid of computers, and that's why he didn't use it. Luckily, he was replaced by a navigator, and things changed. And this guy was sort of playing around with the decision support system comprehensively. Then project where David Lubinsky was involved in, forecasting probability of where the next terrorist attack would happen. This was during the border war, and there was a pattern of how terrorists move through an area. So you use that information and the area where they move through, and what was in the area. Was there houses? Were there any population people? Were there military installations? That kind of thing. And sort of draw a square, a lot of squares on the map and give a priori probability of where the next attack might happen. And we had to go up to Runtu 2 or 3 times. I think maybe David didn't go with me every time to implement the software and train the people how to actually use it. What happened there, which I can quickly share, and I have to be careful with time. We went and slept in the officers' mess, but they didn't have rooms for us, so we slept in a tent with a number of beds. And 9 o'clock, 10 o'clock the first night, there was just a massive sort of machine gun sound, and it sounded like it was right next to you. We got a huge fright. And the next day when we inquired, they said, no, they do this every night because they want to show the enemy that they're still around. For the number of days that we were there, we still couldn't get used to it. It was just quite something that you couldn't get used to. I did a bit of cryptology as well. At CSIR, they sent us all the messages that was picked up or intercepted from the enemy, from the border war, and there was a whole defense team plus CSIR people who tried to break the codes, and I was involved not for a very long time. Then I put it under defense projects. We did a production and distribution model for the prison services. They have, at certain of the prisoners, people that were making clothing, shirts and pants for the prisoners themselves. And, they wanted to know, they knew what the demand was at the various prisons, what the sizes were that was required. So how would you schedule the production to make these clothes and then also to distribute it in a way that is optimized? I know actually very little, I can recall very little of this, but I knew we were involved in that. By the way, why I'm saying that is, in some cases, I still have documents around the projects that we were involved in. The Maize board is the other big project that started at the CSIR. It was possibly the first proper linear programming model that was developed in South Africa. The Maize board, the market for maize was regulated. So all the farmers had to sell their maize to the Maize board. The Maize board then, because of that, knew exactly where the supplies were, and they also knew where the demands were. So they wanted a system that would minimize the transportation cost to get the maize, white, yellow maize, in bulk or in bags to the demand points. Classical transportation model. But there was a twist. And I actually show there what was used to solve the problem, the Apex LP package. Oh, maybe what I should also say is we had an IBM 360 computer, and it still worked with computer cards. You had a punch machine, and you had ladies who punched the program for you on the cards. I had a whole box full and had to load it onto the computer. It took something like 20 minutes CPU time. It used the whole, what do you call it, the complete system, and it could only run overnight. So if you made a mistake, you had to correct it the next day and wait till the next day to do it, which was also something quite interesting. But there was, as I say, in the solution, although it was an optimal solution, you did find that the algorithm couldn't distinguish, if I put it correctly, that where you have two demand points at the same place. You found that the first one on the list gets its maize at a cheaper cost than the second one on the list. although it's an optimal solution. So it wasn't fair to some of the supply points. So we had to make sure that the cost is equitable around, all the supply points. What then came out when we looked at, well, first of all, we used the heuristic to try and sort of overcome that problem. But looking at the actual result, the optimal solution, it was very degenerate. So there was many basic variables that were zero. So what was the thinking? And Theo Stewart actually sort of got the insight saying, well, we need to find the optimal solution that is closest to being the most equitable. So there might be, because it's degenerate, there might be many optimal solutions. Find the one that is most equitable. And during that period, multiple objective programming started developing, and there was something called goal programming. And we said, okay, let's see let's determine and calculate what the goal cost would be for supply points, especially those close to each other. The cost should be very similar, and use that as the goal that we want to achieve, and formulated the problem as a goal programming problem, minimizing the deviation under or overachievement. And the results of the model was actually much, much better than we ever got with the heuristics. So that was quite interesting. And 10 years later, I think one of our colleagues ran the whole problem on a computer, and it took about 20 seconds to solve. Totally different from, what I was used to. And I say, I'm currently, there's something similar still, and that's called location differential, where the market is now totally deregulated, but you still have the problem that there's cost differentials. And I got this from a farmer who farms between Saldanha and Vredenburg, and he said, but it's totally unfair. And I'm looking at it and there's definitely there's an issue there that maybe can be solved with optimization. I have to move a bit faster. The next one is work that we did for the leather industry. They wanted shoe components to be laid out on material, synthetic material, a rectangular piece of synthetic material, or on hide in such a way that your material usage is optimized, that you use as much material as possible, or your waste then is minimized. For hides, there was an empirical methodology developed overseas called standard leather measurement, and that was really aimed at, optimizing the use of leather hides. Ultimately, our system that I'm going to explain now that we developed could be used, but in a manual kind of way. For synthetic material, the component layout system was developed. It's an NPR problem, and we used heuristic to solve it. This work was done by myself and Des Curran. Des was just a brilliant guy, also very good in writing software. So we had to develop a complete system. First, you had to digitize the components, and that you could do in two ways. If the component fits onto the digitizer, you can do it, or you could also do it in components when the component is too big to fit onto the digitizer. Left and right components of a shoe is mirror images, so you only have to do the one side of a shoe, and if you then cut it, you turn the synthetic material upside down and have them both on each other, and you cut only one, but you get both pairs. And then the digitizer, you had to, capture the X and Y coordinates, I think one could also get the center of gravity of the component using the digitizer. Now, then with floppy disks, we entered the components into this system from the digitizer onto the computer. And we had two types of tactics. And I've written it down there, but it might be easier to show pictures. There was A-type tactics and B-type tactics. With A, you could get 8 different sort of solutions. With B, 4, but you could also have mixed tactics. And then there's a lot of mathematics going behind the whole layout of the computers. You have to have the coordinates, you have to have angles of how the component moves. The common components was considered to be, or assumed to be, polygon. You had to be able to measure or calculate the area of the pattern. I mentioned the center of gravity, but there's a whole wrong. I have the manual, but I struggle to read all the mathematics. But it's fairly comprehensive. But just pictures of two systems, and I had to turn it through 90 degrees to get it both on the screen. On the left-hand side, you have the A tactics. Now, the first component is right next to. Can you actually see my pointer?
Yes, we can.
Yeah. So this is the tactic A's. So the first row, you must make sure that the component is right next to the edge, and then you follow a pattern where you turn it around and sort of fit it like that. Then the second row, you try and push the component as high as possible between the two, and so you carry on. The B tactics, and yeah, I'm going through this fairly quickly, but there's a whole range of different ways of placing the components. With the B tactics, every row where you lay them out has to start at the edge of the synthetic material. Using that kind of tactic, this is an example of how the layout would look like. There's another example on the left-hand side where you could actually split the piece of material also in two components and try and fit additional components and using more of the material. The one on the right is sort of, you can see it is the heel of the shoe, but it shows there, you can't see it that well, but there it says what percentage of material is utilized. There it was just under 80% of the material. So we could also show that. There's also on top of that the space sort of between the components, which there it's 0.3 of a centimeter. So all of this was built into the system. Now the question is, did we actually get the shoe factories to use it? Well, those years, computers were quite expensive. They didn't really have the money. So our wonderful system was never really used, which was, quite a disappointment. Okay, then something which I did for my MSc, a linear program for the Purse-Seine fishing industry. Now, it's sort of, there was overexploitation of the resources, fishing resources, even in those days. So how do you make best use of the available resources? This was along the Western Cape Coast. There's pelagic fish, 6 species that I show there. There's 8 fishing grounds, 10 processing factories. I move through this fairly quickly. I'll explain a bit more as we go along. They were using at that stage about 100 vessels with an average capacity of 115 metric tons. The fish was mainly used for fish meal and oil. But if you could if the fish was big enough, you can can it, which was much more profitable, or use it for fish paste. The total landings for the last decade, as I indicate there, was 400,000, and it didn't actually increase. It remained very little, very similar. And most of the fish could only be used for meal and oil. So they wanted a tool to help them manage the resource in a much better way. Here's some pictures. This picture over here shows you what a Purse-Seine net is. The Purse-Seine, no, hang on, pelagic fish. It refers to fish that swims close to the surface of the sea. The other type of fish which swims lower down is called demersal fish, the word over there. But that's the way in which the net that you use. It's like a person, you close it at the top and you have your fish. This is the area. We only considered 6 of the grounds, fishing areas. And yeah, there's quite a lot of factories in the Saldanha, St. Helena Bay area, and there were Hout Bay, Hans Bay, and 10 in total. So it gives you an indication of where it was. The aim was to utilize the resource as best as possible, but preventing depleting the stocks below critical value. I just need to check the time. I'm running out of time. So, there's all kinds of things that had to be considered in the model. The assumptions, I'm jumping a bit. The assumptions were only 6 species, 6 main fishing grounds. The time horizon was 1 year with 12 months periods. And then the fishing age groups were grouped into age classes, and we only considered 5 groups of factories. And there was a whole range of constraints, even constraints where you had to take into consideration that the fish actually grows. So there's age groups, and in the mathematics that I see in my thesis, I wonder where the hell did I get that mathematics from? But it sort of, was required to really get a good feel of what the population is like. And the objective function was to maximize total revenue. As I say, the minimum cost or maximum total profits, the data was just problematic. And this was formulated as an LP model. And I referred to something which I really only saw this morning. There was 3 approaches of solving the LP. You could use a routine or a LP package, and I actually discussed this comprehensively in the thesis that I did, the Danzig-Wolff decomposition. It worked, but it was so slow that we decided that it's not worth it. And that's why the Apex LP package was used. Okay, now I jump to some research. There was a annual NRIMS summer seminar every year, and a different area of the institute had to give us summer seminar, and that was the only one that we gave. You can see multi-criteria decision making was already an area of focus with Theo involved, and he had some people from overseas, Roland Weisdorfer from Germany, Moshe was from Israel, but he actually came from the States. And then decision support was also a big thing, and I did some work around that. Des Curran and Moshe, he was totally sold on ALP. ALP is a programming language, very mathematical programming language. So I'm just showing this to show that we also did a bit of research. And then flowing out of this seminar, we were approached by the breweries to develop a production planning system. And it was really, a decision support system that we developed to help them in their beer production planning, from brewing to packaging and also distribution. They, at that stage, produced all the beer in South Africa. They had 6 different brands of beer, as I indicate there. I think there was 7 different packages. Breweries had 5 regions, the largest being northern provinces. And we did the work for northern provinces. And each province is responsible for their own brewing, packaging, and distribution. The northern provinces had 6 breweries and 15 supply chains. And they did the planning on a weekly basis, based on a sales forecast, and they developed their own sort of forecasting method, which they were using, and it was winter seasonal forecasting model. This just gives you an indication. You start with a sales forecast, then you do the packaging plan to ensure that you have sufficient stock at your various depots. From that, you do a brand pack split to ensure that you have the right packaging at the breweries. Where's my cursor now? And then you do the distribution optimization. You get the inter-depot plan, and you get the brewing plan. And out of that, you can get management reports. Sorry, I'm running through this fairly quickly. Now, all this work was done manually by very experienced planners. But the system just became too complex. I think they built a new brewery in Roslyn during that period. And, handling that manually just became too complex. And that's why they required what I indicate, the interactive menu-driven computer system. We decided on doing a very fast development process using APL. And the idea was to rewrite it later. The look and feel, was something we decided right from the beginning, is to replicate the forms used by the planners. And that, we never had a problem with these experienced people. And one of the guy was in his 50s or early 60s. He accepted the system because everything looked familiar to him. So the optimization was 3 aims: to make sure that there's sufficient stock levels. It should not drop below a certain requirement. The stock would be spread equitably over the depots. And we actually had a method to look ahead using the forecasting. And there was actually an article on this published in Orion. And I think we got the Tom Roswitowski for it. And then also to minimize brewing and distribution cost. Packaging cost is predetermined, so it was not part of the model. As I say, the system minimizes cost, but not to the detriment of depot stock levels. In the end, the system was used for 15 years, all in APL at the time. When we developed a optimization model for distribution the first time, the planners said to us, no, that's not good enough. And we had to go back and relook at our algorithm, and it was faulty. So the point I want to make is people who work in an environment actually know a lot about what they're dealing with on a daily basis. There were a few other projects, and I'm almost there. We were involved in commissioning of the new Groote Schuur Hospital. The building institute of the CSIR was getting involved, and they contacted us and said, well, is there not something that operations researchers could contribute? I actually even went on a course to the UK, 2-week course on the commissioning of hospitals. It was actually very difficult to find, what it is that we can assist with. In the end, we had just something where we said, well, if you break down the old parts or you have to replace them elsewhere, what is the most optimal way of doing that? And that was the effort to try and optimize it. I think we did contribute in the sense that we sat in many sort of committee meetings, and we could sort of ask the right questions and use sort of simple logic to guide them into the right direction. Then allocation of school kids. This was in the Centurion environment with English primary schools. Now, those days we had a feeder system. Kids in a certain area could only go to a certain school. But as the population grow, the kids grow, and they go to high school, so there's less kids going to the school, and the population also changes. New people move in, and the area expanded because of new inhabitants into the area. So with a small sample, it was really just a transportation model again to see how you can optimize the allocation of kids to schools. And it was used by a guy in the Department of Geography for his MSc thesis. We also got a paper out of it. And then the last project is key blocks. You have fault lines in the geological structure of the Earth. Now, one of the mathematicians in NRIMS developed a mathematical way of which you can use these fault lines to see whether when you build a tunnel underground or through a mountain with these fault lines, you might have rocks falling down into the tunnel. And these things was called key blocks. And we developed a system, interactive system, user-friendly system to be used by geologists or geological engineers. And some of them actually used it quite extensively. So that brings me to the end of my presentation. I may be rushed a bit. This is an indication of applied OR work at NRIMS during those years. What I think I have to point out, and that's the beauty of OR, is the areas that you get involved in, the environments. I mean, I had breweries, leather, hospitals, schools, military environment. I mean, that was for the rest of my career, there was always a different sort of area. Most of those I would call classical OR problems. Things have changed now, and I think a lot of the classical OR work is done by non-OR people or people in non-OR disciplines. From 1986 onwards, and I talk a bit about what happened afterwards, there was no logical home for the OR group. Sitting within the CSIR, you're supposed to do research work, but I say we were a consulting group. Now, that was a word you couldn't use in the CSIR because you couldn't be seen to be competing with the private sector because you get government funding. But in some years, our group only got 15% of our annual budget from government funds. So we had no choice but to compete with consultants. What we did try and do is to get involved in complex and difficult projects. There I can mention something Elspeth Dixon, maybe some of you might remember. She said, we get involved in projects where you feel like you're hanging onto a windowsill and you desperately try and just stay alive. And then I also said we needed the bread and butter projects just to keep sustainable. And then lastly, I think one of the big things in my life was I had the privilege to work with really, really top people. And then I want to end off with a quote I saw the other day, which I thought might be appropriate. And this is Salman Rushdie. You might know that he was stabbed by somebody. He lost one eye, and this is what he said afterwards. Those who do not have power over the story that dominates their lives, the power to retell it, rethinking, deconstruct it, joke about it, and change it as times change, truly are powerless. Now, I did joke about a few things. Hopefully, Some things possibly over time you change your view. But yeah, that's it from my side. Thank you.
So thank you for participating this evening, and we are looking forward, Hans, to maybe a next presentation or a next article or something from your side.
Yeah, but thanks very much for the opportunity. I appreciate it.